on developing the complex number system and basic operations. So if you remember, in our first two videos we had introduced the natural numbers to begin with, and then we introduced the most basic operation on the natural numbers, the operation of addition, and then we reversed addition by subtracting. Subtracting then led us to expanding the number system to the whole numbers and then to the integers. And so we talked a little bit about what integers are. Then from there, that was basically the first video. The second video, from there we talked about how we can repeat addition and it becomes the operation multiplication. Reversing multiplication makes the operation of division, and division required us to further expand our number system to the rational numbers. Along the way we learned various properties of addition, subtraction, multiplication, and division. And in this video we're going to also extend. So just as multiplication was repeated addition, exponents are going to be repeated multiplication. And we're going to reverse exponents to get radicals. That's going to lead us to expand our number system further to the real numbers and the complex numbers. We're going to talk a little bit about order of operation as well. So, if we want to take multiplication, we see that multiplication in its most basic definition with natural numbers is just repeated addition. Well, in a similar manner, we can repeat multiplication over and over again. In other words, repeatedly multiply by that same number over and over and over and over again. And we have a shorthand notation for that. It's called an exponent, power, or logarithm. So those three words are basically synonymous: exponent, power, and logarithm. We'll come back to the word logarithm quite a bit in our, I guess it'll be our fourth unit probably. Most of the time we'll call them exponents and powers, but those three words are synonymous. So we use a superscript to denote an exponent, and when the exponent is a natural number, it indicates how many times the base is used as a factor in a repeated multiplication. For example, 2 to the third power is 2 times 2 times 2. So the base is 2 and the power or exponent or logarithm is 3. And so the logarithm or power or exponent tells us how many times we repeat the base as a factor, and then we perform the multiplication. So this says we have 3 2's all multiplied together. 2 times 2 times 2. Of course, that's 2 times 2 is 4, times 2 more is 8. Notice that if we switch these, 3 and the 2, now we make 3 the base and 2 the exponent. That means 3 times 3, which of course is a different operation. But not only is it a different operation, it has a different answer this time. 3 times 3 is 9. So notice that 2 to the third is not equal to 3 to the second. So we see that the base and exponent do not commute. I should say commute, not compute. So we do not have a commutative property here for exponents, like we did for multiplication and addition. In our third unit, we will come back to the properties of exponents and develop them in a lot of detail and extend them to especially rational number exponents and a little bit about real number exponents. And there'll be more videos and things about there that'll develop these concepts and do some more advanced problems with their use. But we will derive some of the most basic properties of integer exponents in the following pages. And we're going to do this by the way of looking at some examples. So if we take a to the third times a to the second, a to the third means a times a times a to the second means a times a. Well, if you multiply all that all together, we can regroup and do whatever order we want. Ultimately, we get a total of 5 a's repeatedly multiplied together against each other, and of course that is just what we mean by a to the fifth. What's the shortcut from getting from a to the third times a to the second and getting to a to the fifth? Well, it's just a to the 3 plus 2. And this can be generalized now. If you have n a's multiplied together and multiply that by m a's multiplied together, you have a total of n plus m a's all multiplied together. So, a to the n times a to the m equals a to the n plus m. So in other words, if we, rephrasing that, if we have two things we're multiplying together with the same base, we can simply keep the same base and add the exponents. Or if we use the other words, if we have a product of two things here with the same base, the power on the product is the sum of the two powers. Or if we say it again, the logarithm on the product is the sum of the two logarithms. Different words for the same thing. Going on to the next one, a to the fifth over a to the third. Well, again, a to the fifth is 5 a's multiplied together. A times a times a times a times a. And a to the third power is a times a times a. Well, we know about fractions that you have 3 a's in the top multiplied together, 3 a's in the bottom multiplied together. Those things basically cancel each other out. That's the fundamental equivalence property of fractions. So this is a times a over 1, or just a times a, which is a to the second. What's the shorthand or shortcut to get there? Well, you could have just taken 5 minus 3 in the exponent. So in general, this can be extended. So if we have a to the n over a to the m, it's a to the n minus m power. So we can subtract powers there. We'll come back to that one in just a minute. A to the third, then raised to the fourth power. Well, if you think about the outside thing that we do is raised to the fourth power. So it says whatever that fourth power is on should be treated as a factor 4 times. Well, that fourth power is on a to the third. So we have an a to the third times a to the third times a to the third times a to the third. Well, what do we do with these? We're multiplying this. It's a to the 3 plus 3 plus 3 plus 3. We're just adding all those exponents. But of course, the shorthand for adding all those exponents is multiplication. So we have 4 3's. That's a to the 4 times 3, or 3 times 4, which is a to the 12th. So it turns out in general, if you have a to the m, a to the n power, raise that whole thing to the m power, power to a power, you just multiply the two powers and keep the same base. So that's a to the n times m power. Okay, what if we have a times b and then cube it, raised to the third power, that is. So that means you take whatever's to the third power listed as a factor 3 times. So it's ab times ab times ab. Well, now, multiplication is commutative and associative, which means we can do it basically by repeated applications of the commutative and associative properties. We can group this together in any order and any grouping we want. So that we can put all the a's together and all the b's together, and we see we get a to the third times b to the third. And of course you can generalize this. So a times b, quantity to the nth power, is a to the nth power times b to the nth power. Now, these properties and the ones coming later will work for any possible natural numbers, and we're going to want to extend them so that they're going to work for any real numbers, actually any complex numbers ultimately. But there are a few exceptions, and the exceptions are, remember, we cannot divide by 0. So if the a is 0 here, we have some problems. Other than that, we're in pretty good shape. Okay, so if you have a over b to the third power, that's a over b times a over b times a over b. Now remember how we multiply fractions. We just multiply numerator times numerator and denominator times denominator. So this becomes a times a times a over b times b times b, or in other words, a cubed over b cubed. And so a over b to the n is a to the nth power over b to the nth power. Now, one of the problems that we might have with property number 2 here is this subtraction, n minus m, might give us a power of 0 or even a negative number. So how do we, if we have that, we cannot interpret it as a repeatedly a factor of a negative 2 times, for example. A to the negative 2, what does that mean? We can't think of it as repeated multiplication anymore. But we can apply the rules that we have above to get a meaning out of this. So let's look at this example. If you have a to the third power over a to the fifth, that's a times a times a over a times a times a times a times a. 3 of those a's in the numerator cancel with 3 in the denominator using our fundamental equivalence property for fractions, and so we get 1 over a times a, which is 1 over a to the second. So that's what a to the third divided by a to the fifth has to be, based on just basic information of repeated exponents for natural number powers and what we know about fractions and reducing them. On the other hand, Rule 2 above says a to the third divided by a to the fifth should be a to the 3 minus 5, which is a to the negative 2. Therefore, if that property is going to work, a to the negative 2 has to be 1 over a to the second power. So in general, we'll define a to the negative n to be 1 over a to the positive n, and that gives us a meaning for powers. One of my friends called this the ninja property of negative exponents. So this ninja exponent here will flip whatever it has hold of. So it'll flip this a over 1 into a 1 over a. And of course it's still got the n power. Of course this ninja property loses its ninja powers after one flip though, because then it becomes a positive power. And here's our ninja property working again. We have this a in the bottom with a negative exponent becomes a in the top with a negative exponent. So 1 over a to the minus n is a to the n. Here's our ninja property working again. A over b to the negative n, using one of the properties above, that's a to the negative n over b to the negative n. A to the negative n is 1 over a to the n. B to the negative n is 1 over b to the n. And if we take top and bottom by multiply by a to the n over b to the a to the n times b to the n in the top and bottom of this fraction, that's our fundamental equivalence property, says those fractions are equal. And now the a to the n's cancel on the top, the b to the n's cancel on the bottom, and we get b to the n over a to the n. Or another way to say it is b over a to the n. So here's our ninja property working here again. Wow! Flips this thing over, and now the b goes to the top and the a goes to the bottom, and there we have our little power becomes positive. Okay. What about a to the n divided by a to the n? Well, as long as a is not 0, that's going to be anything divided by itself is 1, except for 0 divided by 0, which is undefined. But on the other hand, a to the n over a to the n should be a to the n minus n, which is a to the 0 power. And so that says a to the 0 power is 1 if a is not equal to 0. 0 to the 0 power is actually undefined. 1 to the n power is 1 with no exceptions. 1 to any power is 1, and this is going to be true even if we go into, say, any real number power, n. 1 to any power is going to be equal to 1. No exceptions to that. 0 to any power is 0. Well, not quite. 0 to any positive power is 0. 0 to the 0 is undefined, and if you think about it, it's sort of the same problem as 0 divided by 0. We can't narrow it down to a single good answer. According to property 9, 0 to the 0, if we didn't have this restriction, 0 to 0 would be 1. But this property would say 0 to 0 is 0. And those don't match up, so that's a little bit of a problem. And so we don't define 0 to the 0 power. And 0 to a negative power, like 0 to the negative 1 power would be 1 over 0, and that's undefined. That's basically dividing by 0. So 0 to a power is undefined for negative powers and for 0 power. That should say less than or equal to 0. I'll fix that before I get the printout on the handout. So if n is greater than 0, then this is true. It's undefined if n is less than or equal to 0. And again, the same errors here. I'll fix that. So there's a summary of these properties of exponents. So let you try a few properties, a few little exercises that use these properties. So see if you can rewrite these expressions using only natural number exponents and simplify as much as possible. We're going to assume that there's no division by 0, so everything's defined in these expressions. Let me give you a few minutes to work on these and then come back. Press pause now. Okay, most of these can be done actually in your head with a little practice. X to the 5th times x to the 7th is x to the 5 plus 7. 5 plus 7 is 12, so that's x to the 12th. X to the 5th raised to the 4th power is x to the 5 times 4. 5 times 4 is 20, so that's x to the 20th. Here, because of it's all multiplication, we can regroup. We can put the 3 times 5 together, and that's 15. X squared times x to the 5th is x to the 2 plus 5, x to the 7th. And we add exponents here when we're multiplying the y's with the same base here. Y to the 4th times y to the 8th is y to the 12th. So that's 15 times x to the 7th times y to the 12th. Here we can think of the 4 as 2 squared, and the 6 is 2 times 3, and we can basically cancel out like factors. One of these 2's cancels out with the 2 in the bottom, and so it leaves a 2 in the top. The 3 doesn't cancel, so that's in the bottom. The x's, we've got more in the top than the bottom, so we can cancel 5 of those x's in the top with 5 in the bottom. That leaves 10 minus 5, or x to the 5th, in the top. 12 minus 8 is 4, so we're left with 4 more y's in the bottom than the top, so we can leave that y to the 4th in the bottom. We could also rewrite this with the 3 to the negative 1 power and the y to the negative 4th power if we didn't want fractions. The directions said to use natural number exponents, so no negatives. So 3 times x to the negative 4 is 3 over x to the 4th. 3x squared over 5y to the negative 2. First we use our little negative power here, turned it into a positive power, and flips this thing over, 5y over 3x squared. Now we raise each factor to the second power, 5 to the second, y to the second, 3 to the second, x squared to the second. 5 to the second is 5 times 5 is 25, 3 squared is 9. This is, of course, y squared, and x squared squared is x to the 2 times 2, or 4 power there. Now we come to the part that we've done a couple of times before now. We want to do this idea of doing and then undoing stuff. So if we're doing something as an exponent, what would be undoing it? Okay, what's the inverse operation of raising a number to an exponent? We call this inverse operation a radical or a root. So the inverse operation of x to the 3rd power, x cubed, is the cube root or 3rd root of x, or the 3rd degree radical of x. And we use this symbol here. Because we want to extend the ideas of exponents to include rational number exponents in such a way that the properties on the previous slide are still valid, it turns out that radicals are equivalent to using fractional exponents. So what do I mean to say a cube root is an opposite operation or inverse operation of cubing or 3rd power? That says if I do one and then the other, I'm back where I started with. So if I take the cube root of x and then do the cube, I'm back at x. But notice that's also true if I take x to the 1/3 and then cube it, I'm back at x again, because when I multiply these two powers here, 1/3 times 3 is 1, and x to the 1st is just x. So the cube root of x, or the 3rd root of x, is the same as x to the 1/3 power. Now, in general, if m over n is reduced, that is, the greatest common divisor of m and m, or greatest common factor of m and n is 1, then if you take x to the m power and then take the nth root, that's the same as raising x to the m over n power. So this lets us know what we mean by fraction exponents. There also can be written as roots. So we're going to come back to this idea quite a bit more in Unit 3, and we're going to work with fractional exponents and radicals quite a bit in that one, in that unit. For the moment, all we really need is just a square root to make our point for what we need now, which is a 1/2 power. So we're going to look at closure. Is a set of rational numbers closed under exponents and roots? So, like I said, we're just going to look at a square root for right now and not worry about the other powers, or in other words, a power of 1/2. So some square roots are in the natural numbers. For example, the square root of 4, which is really should say the principal square root of 4, or 4 to the 1/2 power, is just 2, because 2 to the 2nd power is 4. Well, that's just in the natural numbers, so no problem there. But what I want to do now is consider the square root of 2, or in other words, 2 to the 1/2 power. Now, is that a rational number? Are the rational numbers closed if we just take a second root? Well, let's see. Okay, or take powers, so that's a rational number power. Well, let's just suppose it is a rational number. If so, then there exist natural numbers p and q such that the greatest common divisor of p and q is 1, and the square root of 2 equals p over q. We'll multiply both sides by q, and we get q times the square root of 2 equals p. And so that means if those two sides are equal, then their squares are equal. So q times the square root of 2, quantity squared, equals p squared. So that says, of course, the square root of 2 squared is 2, and the square root of q is, the square of q is q squared. So we get 2q squared equals p squared. Now, we're going to make use of a very important result in arithmetic. In fact, it's called the fundamental theorem of arithmetic because it's so important. And that is that we can write natural numbers in a unique way as a prime factorization. You can think of numbers as natural numbers as being composed of a bunch of prime numbers multiplied together. And this can be done in a unique way. So if we wrote out the prime factorization of the left and right side of this equation, and let's count how many 2's are in that prime factorization. Okay? Well, because of the square on the p, however many factors, whatever power is on 2 for the prime factorization of p, the prime factorization on p squared will have 2 times that. So we have an even number of 2's on the prime factorization of the right side. Similarly, you've got an even number of 2's in the prime factorization of the q squared. But now we've got this one extra 2 on the left. So that means we've got an odd number of 2's on the left and an even number of 2's on the right. Well, there's no way that that can happen. So we've reached a contradiction. And the only where we've made an assumption in the whole attempt at a proof here was that square root of 2 was a rational number. So that supposition must be false, and so square root of 2 is actually an irrational number. So there's an example of a number which is a very legitimate number. If we take a square whose sides are length 1, then the length of the diagonal from corner to corner to opposite corner there, it's going to have length of square root of 2. So it's a very real length, but it's not a rational number. And so we find that the set of rational numbers is not closed under powers or roots. So once again, what do we need to do? We need to expand our number system. So square root of 2 will have a decimal expansion, and decimal expansions, all decimal numbers, will have some location on a real number line. Okay? And we've seen that decimal numbers, or decimal expansions of numbers, that either terminate, so they end with an infinite number of zeros, basically, or they repeat, end with the same number repeated over and over again infinitely many times. Those are rational numbers. But there are decimal expansions that neither terminate nor repeat, and we've just shown that square root of 2 is one of such number. And these numbers, decimal expansions that go on forever without a repeating or terminating pattern, are called irrational numbers. Not because of any kind of inability to reason or whatever. It's because rational numbers can be put in a ratio, and irrational numbers cannot be put in a ratio of integers. So radicals often produce such numbers. Square root of 2 is an irrational number, cube root of 3, cube root of 4, 7th root of 15. Those kinds of numbers typically are going to be, most of the time, irrational numbers. Here's another example of an irrational number: 0.1, 0, 1, 0, 0, 1, 3 zeros and a 1, 4 zeros and a 1, 5 zeros and a 1, 6 zeros and a 1, and so forth. There's definitely a pattern here, and by examining the pattern, we can figure out what any particular digit we want, any particular digit is. It's either a 0 or 1, and we can figure it out by the pattern. But notice this is not a terminating pattern, and neither is it a repeating pattern. So this is an irrational number. There is no fraction that's going to equal this particular one. Now if we stop this at any particular point, then we get a terminating decimal, and of course that would be a rational number. It would be a fraction. But the fact that it goes on forever without a repeating pattern or terminating pattern, then that is an irrational number. So notice there's no overlap between the irrationals and the rationals, but if you put them together, you get the full set of what we call the real numbers, and that's all locations on a solid number line. So now finally we have a true number line, a solid number line. It does go forever left and forever right, but now we've filled in all of the spaces. The rational numbers filled in many of the spaces between the integers, but now the real numbers fill in all the spaces. So every real number, there's a point on the number line, and every point on the number line there is a real number. So in fact, we formally actually define real numbers as limits of a sequence of rational numbers, and basically you can think of it, you can actually think of them actually as a limit of sequences of terminating decimals, actually, because if we stop this and terminate it someplace, we have a terminating decimal, which is a rational number. But if we keep going and add more and more digits in some pattern, but not necessarily a repeating or terminating pattern, then that's going to eventually approach, and we do this forever, we get a number that's a real number. So, have we gone far enough so that we can get closure now? Can we take all exponents and radicals and roots and things? Well, let's just take again the square root and consider that. And consider something called, what would happen if we take a pretty simple one, like the square root of -1, or -1 to the 1/2 power. Well, whatever this number is, when we square it, we ought to get -1. However, this presents a problem, because if we take 0 and square it, square, by the way, means just second power, because it leads us to an area of a square. Okay? And so the square of 0 is 0. If you take a positive times a positive, you get a positive, so square of a positive is a positive. A negative times a negative is also positive, so the square of a negative is positive. So anytime you take any real number besides 0 and square it, you get positive, and if you square 0, you get 0. You never get a negative, and certainly you never get -1. So whatever this number is, it's not a real number. So the set of real numbers is not closed under square roots. Guess what? We've got to make our number system a little bit bigger. This is the last step we're going to take here. And so we need to be able to throw in this square root of -1, which we're going to call our imaginary unit I. So our imaginary unit I is defined to be the square root of -1, or -1 to the 1/2 power. We can define the set of imaginary numbers to be numbers of the form b times I, where b is a real number but not 0. So 3i, 4i, 5i are imaginary numbers. Square root of 2i, pi I, -7i. Those are all imaginary numbers. 0i is not imaginary numbers, because 0 times anything still needs to be 0, and in fact it is. So 0 times I is just 0, which is a real number. That's why we want to leave out 0 here. Now the set of complex numbers actually is bigger than the set of imaginary numbers or real numbers, and it is all numbers of the form a plus bi, where a and b are any real numbers including 0, and I is again the square root of -1. So that's what this says here. The set of complex numbers, little boldface C, is the set of all numbers of the form a plus bi, vertical line is such that A and B are elements of the set of real numbers, and then I is the square root of -1. Okay, so notice if B is the real number 0, then we just get A, which is a real number, so the complex numbers, this part with the BI goes away, the complex numbers include the reals. And if the A is 0 and B is not 0, then you get the BI, you get the imaginary numbers. So the complex numbers include the imaginary numbers and the reals, but other numbers as well. So if you take a number like 3 plus 4i, that's neither real nor imaginary, but it is a complex number. Now when you have a number in this form, a complex number like 3 plus 4i, the A plus bi form, the A is the real part and the B is the imaginary part. Not the BI, but just the B. So the real part of a complex number is this real number A, And the imaginary part is actually also a real number. It's the number b. So 3 plus 4i, 3 is the real part, 4 is the imaginary part. So we can represent all the real numbers as points on a number line, and so this is our real number line here is like the horizontal axis, like the x-axis, and is the a-axis. It's the real axis, and so we can find numbers here like these red dots are. There's the point. That's the number 0. There's the number 1. Here's the number 6. Okay. But then we can put an imaginary axis. The numbers on this axis, except for the one at the origin, are imaginary numbers. So this is a number negative 3i, or 0 minus 3i. And then we can locate points out here in the plane for complex numbers. So 4 plus 2i, you just graph the ordered pair 4, 2. And so that dot there, it lines up with 4 on the real axis, and it lines up with 2 on the imaginary axis. And so we can locate points in a plane as representing graphs of complex numbers. Okay? And it turns out that the set of complex numbers is very, very nice. Okay? Basically, without proving this now, we may come back to a certain amount of this later. It turns out that we can basically do all the basic things we'd like to do and get it closed in the complex number system. Add, subtract, multiply, divide, powers, and roots all are closed in the complex number system except for a few exceptions that all involve 0. 0 to the 0 is undefined. In fact, 0 to any power with a negative power is also undefined. 0 divided by 0 is undefined. In fact, anything divided by 0 is undefined. So all of these are undefined expressions. Pretty much other than that, things are defined in the complex number system. Now, consider an expression like 3 plus 4 times 5 to the second power. We have a total of 3 different operations here: addition, multiplication, and an exponent. So it's sort of a 3-operation expression. Now, what does this mean? Well, with the 3 operations, there are many different orders they might be performed in. Okay, so some of the examples that could be like this, the parentheses here is used to force the order. So if we did it in the order it comes, to add the addition first, then the multiplication, then the power, that would be like this first line. 3 plus 4 is 7, then 7 times 5 is 35, and then 35 to the second power is 1,225. But that's not the only order we could do. We could add the 3 and the 4, and then to get 7, do the 5 square, which is 25, and then finally do the multiplication last. We could do the multiplication first and the addition last. We could do 4 times 5 is 20, 20 squared is 400, and then add the 3 last to get 403. Or we could do powers first, then multiplication, then addition, and that would be 5 squared is 25, 4 times 25 is 100, then finally add the 100 plus 3 and get 103. Well, this is just an unacceptable situation. Here we have 4 possible answers for one problem. That's just not acceptable. We need to have mean one thing by this. Okay? So we need to establish an order of operations when there are no grouping symbols present. We don't really want to have to write all these grouping symbols, or we need to know what's meant if we leave them out. Well, we actually already have an order that's inherent if you think about it. Exponents are just repeated multiplication, at least for natural numbers. Multiplication, again, of natural numbers is repeated addition, and then addition is your basic root operation. So we could rewrite exponents as multiplication, we could rewrite multiplication as addition, and finally do all the addition. So there's a natural order there. Exponents first, then multiplication, and then addition. And we can keep this same natural order even if we're not talking about natural number operations, but rather any operation. Now, if you think about it, one way we can think about subtraction is really addition. It's addition of the inverse, of the additive inverse. So we can actually rewrite subtraction as a addition problem if we rewrite it with adding the opposite thing, okay, the opposite sign. Similarly, we can rewrite division as a multiplication problem if we think of it as multiplying by the multiplicative inverse. The multiplicative inverse is also known as the reciprocal. So basically, whatever the number is you have in the numerator, flip it to the denominator. So you're basically flipping it over here for the reciprocal. Roots, or radicals, are another way of just writing exponents if we allow fraction exponents. And so if you want to think of it, really radicals or roots really are just exponents, fraction exponents. Division really is multiplication by a fraction, a reciprocal. Subtraction really is addition, but of the opposite sign. So basically you really just have, you can rewrite everything as either addition, multiplication, or an exponent, and then you have a natural order. Exponents first, then multiplication, then addition. That is the natural order of things. So if we take this problem here, 3 plus 4 times 5 to the second power, no other indication to do anything out of the natural order. We would do things in the natural order, which is powers first, 5 squared is 25, then multiplication, 4 times 25 is 100, and finally do the addition last. 3 plus 100 is 103. So 3 plus 4 times 5 squared actually equals 103. I believe that was the last one on the previous slide. But now sometimes we would rather get one of those other answers. And so then what we have to do is we have to force the operations to be performed in an order different from the natural order. Something different from exponents, multiplication, and then addition. And so if we force it by some sort of grouping symbol. The most common one is a set of parentheses, and the parentheses say, do what's inside the parentheses first, get it to a single number, then do what's outside the parentheses. Sometimes when we have nested levels of parentheses, rather than using parentheses for all of them, we'll change one set to brackets, which are these square things, or braces, which are the curvy ones, the same ones we use for sets. Now sometimes these symbols are used for other things, like the curvy ones are used for sets, the square ones are used for some interval notation. But in terms of grouping symbols, these are all the same. You have a beginning and ending of your symbol for your group. But now these are not the only grouping symbols. A horizontal fraction bar, a radical sign, and absolute value signs are also grouping symbols. Let's take the absolute value. Absolute value is not just a grouping symbol, it actually has something that you do. But it's also a grouping symbol. It says take everything that's inside the absolute value and get it down to one number. Then take the absolute value. Okay? Again, the radical, whether it's a square root or third root or fifth root, that's also a grouping symbol. It's not just a grouping symbol, but it is a grouping symbol. It says take whatever is underneath that radical sign, that root sign, that's called the radicand. Get that radicand down to one single number. Do whatever operations are underneath there first, then take that square root or cube root or whatever it is. And a horizontal fraction line is also a grouping symbol. Now, by the way, it's also a division symbol, but a slanted fraction or the little line with the two dots division symbol, those are also divisions, but those symbols are not grouping symbols. A horizontal fraction is a grouping symbol, and it says take the numerator, the top, get it down to one single number. Take the denominator, the bottom, get it to one single number. And only when you get a single number in the numerator and denominator, then you do the division. And so it is a grouping symbol as well as being a division symbol. One of the things that's important with working with order of operations is that you understand the structure of this and understand when you see an expression written out, what order those expressions are supposed to be performed. And so this becomes an important part of understanding how expressions are built up and what they mean, and understanding the structure of each part of the expression and in the expression as a whole, and deciding what part of it we work with first. So Once again, here's the order of operations. Grouping symbols will supersede or take precedence over the natural order of things. And we see several examples, and there may be others, but those are some there. And then we have exponents and radicals first, then multiplication, division, and then addition and subtraction last. Okay, well that concludes the third video in which we looked at multiplication. We used multiplication to get us to talk about, we did that in the second video. The third video we did exponents, and we saw exponents as repeated multiplication, just as multiplication was repeated addition. Then we generalized the properties of exponents a little bit. We derived a few of the basic ones, at least for natural number exponents, and then using those and extending those to integers, we found out some properties of integer exponents. We even made a little bit of sense out of what a fraction exponent would be, and use an alternative notation for fraction exponents called radicals or roots. And so we were able to reverse exponents a little bit. But when we did this, we needed to expand our number system once again, and this time we went out to the real number systems, and then finally all the way out to the complex number system. Turns out that the complex number system is about as far as we need to go. We'll come back to how we can actually do operations in the complex number system a little bit later on, and we'll learn a little bit about the complex number system later on in this course. But for now, that will finish us up for this video. On the next video, we're going to kind of summarize a lot of the things that we've done. I'll have a few good graphics to put in there, and I don't think I put it in the video, but the slideshow will also have, your handout will also have a list of some goals and objectives and kinds of things that you should be able to do after you work through these videos and then practice them a little bit.